So in today's class we will discuss about modes of operation of block ciphers. So what we have studied till now is essentially what are the basic descriptions of block ciphers like DES and AES. So we know that they operate upon blocks, right? So blocks of plain text. So maybe it operates on blocks of say 64 bits, multiples of 128 bits and so on, right? But in normal practice, what we see is that when we encrypt say files, for example, then they are not necessarily multiples of 128 bits or say 64 bits, okay? And also it's obviously more obviously you will expect that you have got large chunks of data which you have to encrypt, right? So in such kind of scenarios, so once you have devised a block cipher, in what particular mode do you apply them so that you can actually encrypt more than the given block of data which is as per specification of the block cipher, okay? So that is what we will try to treat in today's class. So therefore the objectives, we will first of all try to understand certain basic modes of operations. So they are commonly known as electronic code book, cipher block chaining, then there is cipher feedback block ciphers and output feedback block ciphers, then there is something called counter modes, and then we will conclude with a more modern kind of mode description which is in context to disk encryption, okay? So therefore there is something which is called tweakable modes of encryption. So we will also try to address these issues, okay? So therefore, as I told you that the needs for modes of block ciphers mainly arises because of the fact that in normal life your plain text is actually quite large, right? So it's not obviously less than the block size as per specification of the block cipher, and it's also not general that it will be a multiple of the block size also, right? So therefore the idea is that how do you encrypt such kind of plain text, for example, okay? So the normal the very obvious solution would be applying what is known as the electronic code book, okay? So therefore what is electronic code book? So I will come to that, but these modes were essentially first of all standardized by FIPS, which is a body for standardization, and it was done in around 1980. So you can see that 1980 means it dates back to around after DES was proposed around 1977 or so. So it was once DES was proposed, after that these modes of operation came into literature, okay? So therefore what is electronic code book? So I think all of us have probably got an idea that what we will do using our common sense is that so if we have got a large data, then what we will do is that we will break it in chunks of say n bits, right? And then you take the first chunk and encrypt that, obtain the first ciphertext. Similarly, take the second chunk and obtain the second ciphertext, and so on, right? So you can keep on doing such kind of things, and therefore this naive use of the block cipher is what is commonly known as the electronic code book, okay? So therefore in this case you will find that each plain text gets encrypted by the key to a different ciphertext, okay? So if we take the plain text like x1, x2 and so on till xn, then you will find that each of the blocks will individually get encrypted to say c1, c2 or y1, y2 and so on, okay? So what is the obvious weakness in such kind of encryption mode? The obvious weakness would be that if x1 is equal to x2, then y1 is always equal to y2. That means if I take the two similar chunks of data, then they will always get encrypted to the same ciphertext, okay? So that is a weakness. Why? Now because if you see that if there is very less entropy in your plain text, that is the choice of plain text is fairly clear, then actually this leaks almost all the information. Like for example, if you can I will come to a more practical example of this, but this is how the schematic diagram looks like, and it's pretty simple, right? So therefore what it does is that it takes xj, okay, and then it applies this encryption function e and obtains the corresponding ciphertext. So this is as simple as what we know as the basic definition of block cipher, right? In order to decrypt, what we do is that you take the ciphertext block, apply the decryption algorithm and obtain the corresponding plain text. So this is very simple, right? So electronic code book is a pretty straightforward way of handling this problem. But let us note certain properties in order to understand more about these mode, okay? So for the first property that we see is about the error propagation. So you see that so error is very common. So therefore why is this treated quite given a special attention is because when you are transmitting, right, a ciphertext, then it can happen that there are errors in the ciphertext because of communication, right? So now the idea is that if there is a say single bit error in the ciphertext, then what is the impact at the receiver end? how many plain texts are wrongly deciphered. Okay. So in order to see that, what we see is that in this particular case, when there is a single bit error in transmission, then it can create errors in several bits in the corresponding plain text block, but the point to be noted is that only that block gets affected, right? The other blocks are independent, so therefore they have got no effect whatsoever. Okay. And several bits are affected because I am assuming that your encryption is a good encryption function. So therefore, if you know, if you remember our avalanche effect and things like that, so more bits are supposed to get affected, right? So this is quite obvious, and so as I told you, the security issues would be like same block always gets encrypted to the same ciphertext. Okay. Now this is a serious weakness for a low entropy plain text space. So what is a low entropy means? Low entropy means what? Less amount of information, right? So therefore, if you assume, for example, that if you are operating upon say 64-bit blocks, consider two scenarios, that two possibilities are possible. Okay. So in general, if I take a 64-bit block, then all possible 64 bits are possible, right? And that's a quite high entropy plain text. So if I reduce the plain text and consider say an extreme case where there are two possible plain texts, one is all possible ones and the other one is all possible zeros. Okay. Now if you apply ECB, then you know that two encryption ciphertexts are possible, right? So therefore, if I give you one ciphertext, immediately you can understand which plain text has been encrypted, right, with a probability of 1. But in a random case, what should have been the probability of identifying? Half, because you have two possible outcomes, right? So therefore, you see that immediately that when we are talking about ECB leaks more information than what an ideal mode of cipher should leak, right? So therefore, we have to do better than ECB. Okay. So what do we do? So therefore, the obvious idea would be, an obvious solution to this problem would be to apply chaining, right? Let's see that whether chaining, like the previous ciphertext, does it, if I if I devise my mode of block cipher in such a way that my previous ciphertext has an effect on my current encryption. Okay. So then probably this problem will be solved. Okay. So one way of doing that is something which is called CBC, or it's called cipher block chaining. Okay. So I'll come to that, but before that, let's address another important property of the ECB cipher. You see that in ECB, suppose you have got lot of blocks of data, okay, and the last block is not exactly n. So which means that the total size of your block size is total size of your plain text is not a multiple of n, right? So in such kind of scenario, what we will do? We will apply padding, right? So therefore, padding means what? The last block you pad with say zeros. Okay. So padding may not be always possible. Why? Now because, for example, you can just consider a simple scenario like maybe you stored the plain text in a buffer and you would like to obtain the ciphertext stored in the same buffer. So which means you do not like to increase the size of your plain text buffer, right? So in such kind of scenario, that is without padding, can I circumvent this problem? Okay. So there was one solution given which is known as a ciphertext stealing. Okay. So we will see how this works. So the idea is that we have to do ECB mode of encryption, but without doing padding. Okay. So what it does is that the idea behind ciphertext stealing is that it makes use of ECB. It makes the purpose is that it makes the use of ECB possible without an additional padding. Okay. So the idea is that the last two blocks, that is Pn-1 and Pn, are actually encrypted slightly differently and also out of order. Okay. So therefore we will try to understand how it works. So what is the problem? The problem is that you have broken your data into blocks and you have got Pn-1 and Pn. So let's consider the last and the last but one blocks. Okay. So Pn-1 and Pn. So assume that Pn-1 has got n bits. Okay. But Pn has got less than n bits, say m bits. Okay. So how do you encrypt in such a fashion that the ciphertext is also an n bit block, is also another, it's also has got the same number of bits. So what is the total number of bits? M plus n. So therefore I do not like to increase the number of bits. Okay. So the solution works as follows. So diagrammatically it will look like this. So consider Pn minus 1 and Pn. Okay. So what is the size of Pn minus 1? N bits. Sorry. And what is the size of Pn? It is m bits, and m is suppose less than n. Okay. You can work with less than equal to also, but let us assume that it is less than n. Okay. So how do I encrypt? So I take this block Pn minus 1, and since it is the ECB mode of encryption, I can encrypt it independently or independent of other blocks, right. So what I do is that I apply EK and I obtain a corresponding ciphertext. Okay. So what is the size of this ciphertext? It is also n bits, right. So now what I do is that I take this x and I divide into two portions. So the first portion is something which I take only m bits, and the remaining portion I take n minus m bits. Okay. So then what I do, I take this Pn and I make a y, I copy these m bits here, okay, and I copy this n minus m bits to this part. Okay. So therefore now you see that what is the size of y? It is also n, right. So therefore now what I can do is that I can apply another independent application of EK on y, right. So therefore what we do is that we take this and we apply EK. Okay. So you operate and obtain another n bit of output. Okay. You obtain another n bits of output. So now, so therefore this output that you obtain, so this is of n bits, right. And what is the size of this? This is actually n minus m, right. So therefore this is actually totally n, but what I do is that out of them I take the first part, that is first m bits, and I call that Cn minus 1, and I take this and I call that Cn. So what is the size of Cn now? Cn is n. So but what I would have liked is that Cn would have been of m bits and Cn minus 1 would have been of n bits. So what I do is that I do a swap. Okay. So what I mean is that the first part essentially has n bits and the second part has got m bits. Anyway, the swap has got no effect finally. I mean, it's just to make it more according to our custom. That's all. So the point what you observe here is that if you apply, if you have got an m plus n bit of input and your output is also another m plus n bits of output. Okay. So this phenomenon is commonly known as the ciphertext stealing. Okay. So how does the decryption work? So I have just given sketched how decryption works. So you see that you take Cn. So I have not in this particular detailing or rather formalism, I have not considered the final swap. Okay. So you see that you take x and you apply EK over Pn minus 1 and you obtain x. Cn minus 1 is the first m bits of x. Okay. And how do you form y? You concatenate Pn, which has got m bits, with the tail, that is n minus m bits of x. Okay. And then you apply your EK function and you obtain Cn. Okay. So how does decryption works? You take this, you apply the decryption function, you obtain y. Okay. So what is Pn? Pn is the first m bits of y. So you can obtain Pn through that. Okay. Now you need to obtain Pn minus 1. So what you do is that you see that you have got y, and y is nothing but Cn minus 1 concatenated with tail, that is the last n minus m bits of y. Okay. So now you see that Pn minus 1 is simply equal to the decay of x. Okay. So x decrypted with k, right. So in that way I obtain both Pn and Pn minus 1. Okay. So this particular process is known as ciphertext stealing. Okay.
With the pattern, we had a problem when we want to have ciphertext and the plaintext in the same buffer. So how's that problem addressed in this ciphertext stealing?
Yeah, so therefore you see that the size of the ciphertext does not increase. Okay, but obviously there is some additional complexity involved, like you have to do some additional operations and maybe also some storages also. Okay, but the point is that I can use the same buffer in which I stored my plain text, which has got say m plus n bits, to obtain an output which also has got m plus n bits. Okay. So, but there is obviously an additional complexity, and also the error propagation property which is there in normal ECB, that also gets changed. So, now you will see that this particular thing does not have got the same error propagation property which was there in the normal ECB. Okay. So, in the normal ECB, if you had affected one bit, only one block was getting affected, but in this case there is a interdependence, right. So, therefore, one block will affect the other block also. So, there are certain changes which have been done here, right. Then there is also an additional complexity involved. It is not, so you can see that an ECB is always like, because you can actually parallelize the ECB mode, right, because all the blocks are independent. You can do pipelining in hardware, you can do lot of interesting things in architecture also, right. But in this case, when you are doing this kind of operation, then obviously you cannot really parallelize. You have to wait for one I mean, you have to wait for one and then do the other, right. They are actually independent, and I mean they are actually dependent, right. So the other way of solving, I mean so we saw that ECB had got certain security problems, and that problem can be solved actually by chaining. Okay. And there are the other modes of block ciphers that we will see essentially has got chaining in them. Okay. So, the first thing that we will consider is something which is known as CBC, or cipher block chaining. Okay. So, why is cipher block chaining used? And it is used to solve the problem of identical plaintext blocks being encrypted to the same ciphertext blocks. Okay. So, therefore, the idea of chaining essentially works as this. What you do is that you take every plaintext block, okay, and you XOR with the previous ciphertext, okay, and then you apply encryption, right. So, you take plaintext I, for example, and you XOR that with the previous ciphertext, and then you apply the encryption function to obtain the present ciphertext. Okay.
What do you mean the identical plaintext?
Identical plaintext means same plaintext. So, in ECB mode we saw that if we had two plaintext blocks which are same, then the ciphertext blocks were also same, right. So, using CBC we will try to solve that problem, that even if two identical plaintexts are being considered, but they will in two time or two values of the indices index I, you will find that two different ciphertext result. Okay. So, what about the initial ciphertext? You know that initially if I don't have any value, because there is, I mean C0 I don't have any ciphertext, right. So, in order to initialize I use a vector which is commonly known as the IV, or initialization vector. Okay. So, this is how it works, and this is the pictographic description of an ECB. So, you see that you have got a previous ciphertext, and this is your current plaintext. You have XORed them and you have applied your encryption function. Okay. Similarly, you take this ciphertext, again feed it back, right. You obtain the next ciphertext, get the next plaintext, XOR that, again apply encryption. So, you keep on doing that. So, you see that even if two same values of X comes, because your previous ciphertext may be different, right, at two different time values, you will get two different resultant ciphertexts. Okay. So, immediately you can see that the problem of ECB gets solved. Okay. But what is the problem? There are certain problems that we will see, but first of all let us see what is an IV. So, therefore, this IV, which is an initialization vector, is actually not a secret value. Okay. It is not like the sender and the receiver has to maintain a secret value of, it is not like the key. Okay. But there are certain problems for which I would not like to reveal the value of IV to an attacker also. Okay. So, rather I will say that what I don't want is that I don't want an attacker to manipulate the value of IV, because if he manipulates the value of IV, then there are certain problems, and I will come to that problem. Okay. So, that problem is commonly known as the authentication problem. Okay. So, therefore, block ciphers are commonly used for authentication also. They are not only used for confidentiality of data, but they are also used for the integrity of data. Okay. So, there is a problem when the block cipher is used, I mean for example, when the CBC is used for integrity of data and the attacker can manipulate the IV. Okay. So, there are some problems for that. So, we will see that. So, the decryption is quite simple. You can see that you just take this, you apply the E inverse, you obtain this, and then you can take the previous ciphertext, XOR that, and obtain the corresponding plaintext. So, you see that in encryption you have applied E, and when you are decrypting you are applying the inverse of E, right. So, therefore, the encryption function and the decryption function requires different algorithms. That is, in one case it's an encryption algorithm and the other case it's a decryption algorithm. Okay, and if the E and the E inverts are not same, then you actually required to make a separate hardware for the sender and the receiver, right? I mean separate implementations. So we'll come, as I was telling you that about the IV based attacks, there are actually many IV based attacks, but I will just give you a common idea what I mean by that. So therefore keeping IV secret is not necessary. It's not necessary that I have to keep my IV value secret, okay, but it is more important that the integrity of IV should be maintained. Why? So you note this, that the first ciphertext you can obtain by EK of IV XOR with P1, right? So suppose, therefore, from if I just rearrange, I will get P1 is equal to DKC1 XORed with the corresponding value of IV. So what does it mean? So somebody, the attacker, for example, if he can manipulate this value of IV, then automatically this plaintext values gets immediately determined, right? For example, if I flip, for example, the first bit of IV, then immediately the decryptor will also get the first bit of plaintext flipped, right? So therefore you will find that in authentication purpose, what we do is this, that is anybody who wants to maintain authentication of data and apply block ciphers for doing that, what he will do is that he will take a message M and apply a MAC or a message authentication code over the value of M and send it to over the insecure channel, right? So the sender takes it and sends it to the receiver. What the receiver does is that from this value of MAC, okay, he takes this value of M, applies the corresponding MAC which he can only operate, which he can only apply, okay, because there is an inherent secret, for example, in case of block ciphers, a key, right, the attacker is assumed not to know the key, right. So therefore he applies this value of MAC and checks whether it meets the value of the MAC which has been received, okay. So that's the idea of authentication. So you see that in case of CBC, when the attacker can actually manipulate the IV, then he can actually doctor the corresponding ciphertext in such a fashion that the plaintext and the corresponding MAC value he can maintain in such a way that although the message has been changed, but still this particular relation holds, right. That is, for the given plaintext, I know another value of a ciphertext without knowing the key, right. He can do that. You see that? So what the attacker can do is this, that is, for example, so he wants to break this, right, somebody who wants to break the authentication, what he can do is that he will just, for example, flip the first bit of IV, okay, and immediately he knows that the plaintext is also flipped by one bit, right. So therefore, suppose the sender sends the value of M, comma MAC M, and he wants to send it to the receiver. So the eavesdropper, he obtains this, okay, and he manipulates the value of M dash by flipping, say, the first bit, okay, and he sends M dash, and he can also obtain the value of MAC. Why? Because he knows that a ciphertext, what he has done is that he has just flipped the value of IV, right. So therefore what he will do is that he will take the same thing and he will communicate that, but what he will do is that he will flip the first bit of IV. So once the first bit of IV is flipped, right, after that this pair will also maintain the relation, right, because he knows that what the receiver will do is that he will take this M and apply the CBC function with the IV flip, because the IV has been flipped, right. So immediately he will also find out that the same this particular relation is maintained, and therefore he will believe that the integrity of data is maintained, but which is not true, right? M has been modified to some other value. So for example, the first bit has been flipped in the plain text, right. So you see that integrity is actually not maintained by these modes of block ciphers, okay, because of this problem of IV. The attacker, if he can manipulate the value of IV, then actually we have a problem.
What is MAC?
MAC stands for Message Authentication Code. So it stands for Message Authentication Code. We can actually apply error checking to solve this problem, right. So initially the people thought that, okay, using one encryption function, can I solve both problems? So can I solve the integrity problem and also solve the confidentiality problem? So we see that in CBC with IVs we have a problem.
for different plain text, different IVs are used.
For different plain text, different IVs are used. So that is the idea. So therefore, you see that immediately from this problem, I see that for different plain text, I would like my IV also should change. Okay. So what is commonly done is that instead of keeping one IV, you maintain a set of IVs, or you maintain a pseudo-random function between the sender and receiver through which you change your IV at a corresponding instant of time. But for the different text, you do not actually keep the same value of IV. Okay. So talking about error propagation again, let's study the error propagation in case of CBC. So you can easily see that if there is a single bit error in the ciphertext block CJ, so consider this, that there is a single bit error in ciphertext block CJ during transmission, like what we have done for the ECB also. Okay. So during decryption, the entire plain text PJ is wrong in most of the bits. You see that because it's again similar to ECB, right? But there is a single bit error in the plain text PJ plus 1 also. Why? So if you see your PJ function, how was your PJ function? How can you write your PJ function? You can write your PJ function by dk of corresponding value of Cj XORed with Cj minus 1, right? How can you write Pj plus 1? It is equal to dk Cj plus 1 XORed with Cj, right? So now imagine that there is a 1 bit error in Cj. So immediately if there is a 1 bit error in Cj, lots of bits of Pj gets corrupted, right? But if there is a 1 bit error in Cj, then only there is a 1 bit error introduced in the Pj plus 1 also. Okay. So you see that there is a 1 bit error in Pj plus 1 because of the XOR function, right? But what about Pj plus 2 and so on? They are correctly being decrypted. So you see that the error propagation is actually restricted to only 2 blocks. Okay. And also, I mean, the rest, there is a 1 bit error actually in Pj plus 1. Okay. So therefore, if you are clever, maybe you can correct that also. Okay. But what about the other blocks? They are essentially being decrypted quite okay. Okay. So therefore you see that there is a restricted amount of error propagation considered. I mean, there is a mechanism in CBC to recover. Okay, and we call this phenomenon as self recovery. It can recover itself. Even if there is a 1 bit error, it can recover giving 2 wrong plain text. After that, the rest of the blocks are decrypted quite okay. Okay. So that's why we say that the plain text block Pj plus 2 to Pn are not affected by this single bit error, and this process is commonly known as self recovery. Right?
So this error in CJ
Yeah.
was because of relaying it.
Yeah, because of communication.
Because if we while encrypting it, if the error is there, then the entire there's a
No,
cascading effect.
what we are considering is a problem because of transmission. Okay, so as I say, during transmission. Okay. So what are the disadvantages of CBC? So immediately you can see that you cannot actually parallelize because there is an amount of chaining involved, right? You cannot pipeline, you cannot parallelize, all these things you cannot do, right? So there is a problem in implementation. So, and that's the cost which you pay for extra security. Okay. So therefore, if there is a scenario like random access of files and you would like to encrypt them, then there is a problem because you see that, I mean, random access files cannot be encrypted because the previous ciphertext is also required. Okay. So therefore, you cannot take a block and encrypt that because you need the encryption of the previous block. Okay. So 2 equal messages encrypted are equal if and only if the same IV are used. So therefore, we would like to keep this IV changed, right? So attacker, and also there is another additional problem that an attacker can actually add some ciphertext blocks at the end of the ciphertext. So if we, because you know that there is a, if I maintain the ordering at the end, I can do some manipulation and I can add on some extra ciphertext at that place, right? So these are some disadvantages, and this is the schematic works. Okay, so therefore you see that. So therefore this particular, so the next block that we will be considering is called a cipher feedback. Okay, so what we have seen till now is CBC. So that was cipher block chaining. Okay, so this is a new mode of operation. It is called the cipher feedback block or CFP. Okay, So what does CFB, how does CFB work? So you see that in CFB what you do is that you take, so therefore you take the value of x, okay. So initially start with IV, okay, you start with IV and you encrypt IV and you obtain a corresponding output, okay. Then you choose the first R bits of this corresponding output and you XOR with say another R bits of the input, okay, and then you take this corresponding ciphertext and you feed it back, okay. So therefore the name cipher feedback, because you are actually feeding back the cipher, okay. But what is the difference with this from the previous mode? So in case of previous mode, we were actually see this XOR was at the top, right. So it was affecting the input of the encryption straight away. But in this case actually you will find that this mode of operation is more like something which is called a stream cipher than a block cipher. So although we have not talked about stream cipher till now, and we will take up stream cipher on the next day's class. So idea of stream ciphers is that, but I probably hinted in one of my classes, is that in case of block ciphers you have got blocks of data, but when the block size is say 1, we call that a stream cipher, okay. And in order to increase the throughput commonly, actually you will see that maybe you are operating not in 1 bits, but you are actually operating on say R bits, okay. So you see that in this case this particular encryption function is used to generate something which is called as the key, okay. So it generates the key stream, okay. So you see that this particular encryption function generates the key stream, and that is being XORed with the corresponding plain text to obtain the corresponding ciphertext, okay. So therefore in this case what another thing which you do is that you take this ciphertext and you feed it back. So how many outputs are here? There are R bits of output, right, because you have taken the leftmost R bits and you have XORed with the X and obtained the ciphertext, right. So then what you do is that you take this corresponding ciphertext and you feed it back to this particular shift register, okay, and then what you do is that you do an R bit shift to this, okay, and if you do an R bit left shift to this, right, then you find that again you have got n bits. So initially you had n bits and finally at each step you are doing an R bit left shift, okay. So therefore this, so what happens is that this CJ comes and sits in the last R bits, okay, and the rest of the bits are being thrown away, okay. So you see that if there is a problem in one of the ciphertext, because I mean we can probably visualize it better at this point, that if there is a problem or again due to communication or transmission, okay, in this particular ciphertext, then what will happen? In case of plain text, it will start corrupting, right. It will obviously corrupt that particular block, okay, but it will also corrupt the following blocks. And how many blocks will it corrupt? It will corrupt as long as the effect of it stays in this shift register. So it will keep on shifting, and at some point, after some point, the effect will be, there will be no effect, right. So therefore in this case not only one particular block gets wrongly decrypted, but actually there are problems in decryption in the following blocks also, until and unless the effect of that gets removed in the shift registers, okay. So you see, you follow this diagram, okay. You see, so suppose there is a problem here, okay. So how many, so you observe that how many ensuing blocks this has an effect. So you see that this CJ comes and is being fed back, and this goes and sits in the last R bits of this particular register. No? So until and unless, I mean, so therefore if there is an error here, there is an error here also, right, and gradually in the next block it again gets shifted by R bits, right. Yeah, so it again gets shifted by R bits. So you can understand that by say n by R, okay, if I assume that n is divisible by R, otherwise you have to do a seal operation. So you will find that in so many blocks, for so many subsequent blocks, there will be an effect of this corrupted block, corrupted ciphertext, okay. So we saw that in ECB mode, if there is a problem in the ciphertext, then only one block is affected. In CBC mode, there was effect in 2 blocks, but in case of this particular mode, which is known as CFP mode, there are actually a problem in n by R number of blocks, okay. So therefore the error propagation criteria is actually poorer, okay. So, but I don't know, I am saying poorer from the communication point of view, but from the security point of view this may be actually an advantage. Okay, so it depends upon what is the current context. So, certain points are that both encryption and decryption functions. So, another point to be noted here is that both the encryption and the decryption uses the uses E. Okay, so therefore there is no application of E inverse in the decryption also. So, implementation wise this would have been easier because I do not require another coding of E inverse, right. I can use the same E function and I can decrypt, right. So you see that there are some advantages and disadvantages, right, always. So they are. So you see that in this case another advantage is that no padding is needed. Why? Because R is normally quite small. Okay, so therefore R is typically say 8. Say for example, Steam ciphers will maybe operate upon 8 bits of blocks. Okay, so therefore you see that since R is quite small, there is no requirement of padding. So there is no problem of no issue of again applying a stealing mechanism to solve the padding problem. Okay, so you see that encryption can start when R bits of the plain text are ready. So therefore immediately when R bits of blocks are have arrived, you can actually start encryption, and similarly for decryption also. Okay. So we have already discussed about this error propagation problem. So again revising, a single bit error in ciphertext block Cj creates a single bit error in the plain text Pj at the same position. Okay, you can see because of the XOR function, and however most of the bits in the following plain text are affected. Okay, and the blocks are affected as long as the effect of Cj is in the corresponding shift register. Okay, and you know how many blocks will actually get affected. So there is another similar mode which is called the output feedback mode. So in our case of CFP, we are actually feeding from the ciphertext output, right? In case of OFP, we do not feed from here, but we feed from this point. Okay, so that is the output of the encryption function. Okay, and consider this scenario. So this is actually quite similar to the CFP mode, but only we have actually fed back from this particular point, and there are actually a lot of differences because of this. Okay, so can you figure out what are the possible differences? So maybe you can observe the error propagation. The first thing which you note is that it remains localized to one single block, right? So therefore you will see that affecting one plain text block affects one ciphertext block only. Okay, so complementing a bit in the ciphertext complements a bit in the plain text. So you see that if I complement a bit in the ciphertext, then that will lead to the complementing a bit in the plain text. Okay, what is the problem? Again, authentication. Okay, so it is not good for usage in authentication, as message authentications can be done ensuring that the MAC, which is the message authentication code, is equal to the output feedback block being applied over the message. So I can again prepare pairs like that, and I can again do problems in authentication. Okay. So there is another mode. This is the fifth mode and the last mode of this family. It's called the counter mode. Okay. So what you do in counter mode is that it's quite similar to the OFP mode, except the difference is in how you are generating the key stream. Okay. So what you do is that you actually make a counter, and in each case you start incrementing the counter by 1. Okay. So you take the counter. So in the first block, instead, say you call that an IV, for example, initialization vector, and you apply that encryption function, obtain the corresponding output, and you obtain the encrypted output, and you exort that with your plain text. Okay. What about the next mode? The next mode is just IV plus 1. Again apply the encryption function, obtain the ciphertext, exort that with the next plain text. Okay. So what is the difference between this mode and the previous mode? You do not require to wait for, say, the previous output to come, because you know that they are counters and you know that what are the corresponding outputs. So what does it mean? You can immediately parallelize all the blocks, right? So you can actually make good implementations for this mode. Okay, and there is actually, you can prove it also, that it's an important requirement that for every plain text you actually choose a different value of the counter. Okay, so your counter values, you should not replicate a counter value. Like for different plain text, you should not use the same counter value. You should always update your counter value, again by applying a mutually agreed upon pseudo-random function or something. Okay, so therefore you see that Ti is equal to this count which I have started with, count plus I minus 1. So the ith stage, this is the value which the T register holds, and I am doing a modulo 2 power n, which means an integer addition. So therefore it's a modulo n bit adder, okay, and up counter essentially. So what you do is that you take xi, you XOR with the corresponding encrypted for output of ti, and you see that the key stream and the ith instance can be computed independently, and therefore you can actually parallelize and make faster implementations. Okay, so hardware or software, you can actually make it quite fast, right? So this is an illustration that actually which shows that the ECB mode is actually weak. So you see this photograph of penguin which has been encrypted using the ECB mode. Okay, so you see that there are traces of the original plain text being there in the ciphertext also, right? So you can see that you can probably say that the ECB mode is weak, but this is an example of other modes, maybe the counter mode for example, and you see that it looks quite random. Okay, so although it looks random, it is not necessarily a good cipher. Okay, but at least we can say that this is a weak cipher, weak mode of operation. Okay, and there are actually historically examples of very weak modes which essentially has got these random kind of things. Okay, so therefore at least it says that this is bad, but it really does not say that this is good. Okay, and this diagram I have taken from Wikipedia. Okay, so you can see that. So let's come to something which is more modern. Okay, so you see that confidentiality and authentication were not provided by the old modes of block cipher. So we have seen that, I mean, when I say confidentiality is not provided, what I mean to say is that both confidentiality and authentication are not provided. Okay, so authentication and encryption I do not get at the same time. Okay, and after this actually an idea came up which is known as authenticated encryption. Okay, so many recent modes have been proposed recently. So for AES for example, so the previous things were mainly devised for DES. Okay, and people have come up with recent modes, and these are some names which you can note, say IAPM, CCM, EAX, GCM, OCB and things like. So you can go to NIST site and you will find a lot of details about modes of block ciphers, recent modes of block ciphers. Okay. So I will rather conclude my talk with a very current context, very interesting topic which is called disk encryption. Okay, so therefore, what is the idea of disk encryption is that you know that your disk essentially has got various sectors, right? So therefore, the objectives would be like the data on the disk should remain confidential, okay, and data retrieval and storage should both be fast operations. So they have to be fast. Okay, so in order to do that, what we do is that we break our disk into something which is called sectors, okay, and operate upon say 512 bytes of data. Okay, so immediately you can understand that you can actually apply, maybe you know that I would not like to apply ECB mode because of the reasons that I told you. So maybe if I apply CBC mode also, for each of these 512 bytes I have to maintain a different value of the IP. Okay, so and also another objective is that the encryption method should not waste disk space. So therefore there should not be a wastage of the disk space, right? Otherwise the user will be very unhappy, right? So the model of the adversary which is very commonly used is this, that is you can actually read the raw contents of the disk at any time, so that the adversary can read the raw contents at any time. He can request the disk to encrypt, okay, he can store arbitrary files of their choosing, and he can modify any unused sectors on the disk, and he can also request for decryption. Okay, so with this kind of power we have to protect our system. Okay, so this is the power of the adversary. So therefore what I would ideally like is that the only information which is leaked is whether the data in the sector has or not been changed since the last time it was being probed. Okay, so therefore I would like to maintain that. So what we will see is that so immediately you can understand that no two such sectors can be encrypted in identical fashion. Why? Because if you see what were the powers of the adversary, what you can do is this, that is the adversary will, so suppose the challenge to the adversary is to decrypt a given amount of data, right? So what he will do is that he will take that and copy that into another sector, okay, and request its decryption, right? So therefore as we have assumed is that the model, in the model of the adversary can decrypt, but decrypt in a different sector. Okay, so in that kind of model, if he does so, then he can actually obtain the information. Okay, and there are practical reasons why the model has been devised in that way. Okay, so therefore this rules out ECB, and also the CBC mode can be used, but still there are some problems, and the problem is again because of the IP. Okay, The problem essentially is again in case of IV. So these particular block ciphers, therefore, I mean, is something which is called, this mode is more commonly known as the tweakable mode of block cipher. Okay. So these attacks are commonly known as the watermark attacks. Okay. So what is a watermark attack is as follows. So what you can do is that all the 512 byte sectors, okay, so therefore what I have told you is that all these 512 byte sectors have different values of IVs. Why? Now because of this tweakable property, they cannot have the same value of IV. Okay, so all the sectors should individually have different values of the IVs. Okay, because why? Because what I would like is that I would like any sector to be encrypted independent of the others, because I want fast encryption, right? So therefore, every sector of 512 byte should be encrypted independently, right? So therefore, if I apply CBC, all these independent sectors should have an independent value of the IV, right? So therefore, now the attacker, what he can do is that he can actually frame two corresponding files, okay, for which the ciphertexts are actually same in the first parts at least. Okay. So what I am assuming is that, for example, the attacker can predict the values of the IVs, okay, because the IV is not a secret value, right, and the attacker can maybe manipulate the value of the IV also. So if the attacker can manipulate the value of IV, he can actually prepare two files for which the corresponding encryptions are same. Okay, that is because if I know the value of say IV1 and IV2, if I consider two sectors, then I can make two initial blocks, and I call them B1 and B2, such that B1 XORed with IV1 is equal to B2 XORed with IV2. So what is the resultant? I apply EK, I obtain the same corresponding ciphertext. So if I can frame such kind of blocks in my plain text, then what is the result? After one encryption, all the sectors will have same corresponding data, right? So therefore, if the attacker, if he sees such kind of scenario, can immediately figure out which that particular file has been encrypted. So you see that you leak some amount of information. You leak that, okay, the attacker is able to identify if he can manipulate the IV, that one of the particular files has been encrypted. Okay, and this number of files actually is not very small, because what he has done is that he has just manipulated B1 and B2, while the rest of the things can be arbitrary, right? So therefore, you can actually make a large pool of such files, and you can figure out that, okay, these pools have been encrypted. Okay, so this attack is something known as the watermarking attack, because it leaves the same amount of watermark. Okay, so you see that the problem is that all the encrypted sectors will be identical, leaking information on the existence of the file. Okay, so this is something similar to the ECB mode of block ciphers. Okay. Well, you see that you can actually make two files whose corresponding ciphertexts will have essentially the first blocks identical, right? So therefore, now if somebody encrypts it, then using this particular property as a signature, the attacker can figure out that these files have been encrypted. Yeah, so therefore the attacker can figure out that these particular files has been encrypted. So what I am saying is that, I mean, this is a model, okay, so the model is like that the attacker is able to force essentially two values, or you can tell with a very high probability that if you encrypt these two files, then these two files will lead to the same ciphertext. Okay, when I am saying same ciphertext, I mean to say two ciphertexts with same starting blocks, okay, starting output blocks. The rest of the blocks will be different because of other things happening. Okay, so this is just an idea. Okay, I am just trying to give you an idea that the previous modes of block ciphers like CBC are not so secure in such kind of scenarios. Say maybe in case of disk encryptions. Okay. Yeah.
Manipulates the value of the plain text before the encryption.
Before the encryption starts. Yeah.
In this case.
Yeah. So the idea is that the attacker can say that these particular two files, if you encrypt, you can actually will find that the output ciphertext has certain properties. But in a random situation, even with those two files, he should not be able to tell any property about the ciphertext, right? but therefore you see that you have a distinguisher, and as I told you that given any distinguisher you can always convert that into an attack. Okay, so first thing is to observe a distinguisher, and we see that we have a distinguisher in such kind of scenarios. Okay, and actually there has been studies on this, and based upon these studies there have been some way outs proposed. I will not go into those proposals, but there are something which is known as special tweakable modes of block ciphers, and there are actually something which is called narrow block encryption and wide block encryption, which are used to solve these problems. Okay, so the other idea would be to make the IV unpredictable. Okay, and this is an obvious solution. What you do is that you apply maybe block ciphers in the CTR mode to generate the IVs. Okay, so maybe you can have a CTR mode to generate the IVs and try to make the IV unpredictable to the attacker. Okay, and this is something which is called an ESS IV, which is also very commonly used. Okay, counter mode. So I will give you some points to think on. For example, that can the CBC decryption be parallelized? You can think that. Encryption, I have told you that it cannot be parallelized. So you can just think on whether the CBC decryption can be parallelized. The other thing could be like changing one block of ciphertext has an influence on two blocks of the plain text, right? So can this be improved? So you can just see, think on this. And how will you do ciphertext stealing? For example, I have shown you for the ECB mode. How will you do ciphertext stealing for maybe the CBC mode? Okay, and the CTR modes need to change the counter value for each plain text, but maybe you can just again think better, like think more deeply why it's required. Okay, so some references which I have used is Stinson's books and Farhausen's book and Stalin's book. So you can read Stinson's book as a quite detailed description on this, and certain papers on disk encryption which I have followed are given in the last two things. Okay. So, next day's topic will be on stream ciphers. So, we will start with stream ciphers next time.